In late November and throughout mid-December 2025, a quiet but profound shift occurred in the scientific story of 3I Atlas. New datasets were released, not with dramatic headlines, but with an unusual concentration of attention from multiple space agencies. This was not about sharper images or more vivid colors. It was about entirely different wavelengths entering the conversation, revealing behaviors that visible light alone could never show. Until that moment, 3I Atlas had largely been treated as a passive visitor, a body reflecting sunlight, shedding dust, obeying gravity, and passing through our system much like countless objects before it. But the new observations changed that framing. The object was no longer simply reflecting radiation. It was interacting with space itself, exchanging energy with the solar wind, responding to plasma flows, and leaving measurable fingerprints across the electromagnetic spectrum. For the first time, an interstellar object showed signs that did not sit comfortably inside existing comet models. The equations still worked on paper, but only by stretching assumptions to their limits. Density estimates became uncertain. Composition models grew fragile. The timing of activity refused to align neatly with thermal expectations. Emission patterns appeared where they were not supposed to exist. This was the moment when 3I Atlas quietly crossed an invisible line. It stopped being just another strange rock from another star system and became a problem that could not be ignored. A problem that forced scientists to reopen files they believed were settled, to recheck instruments that rarely disagreed, and to choose their words more carefully than usual. That restraint, that sudden hesitation in interpretation, may be the most revealing signal of all. When scientists stop speculating out loud, it is rarely because they see nothing. More often, it is because what they see no longer fits cleanly inside the language they trust. So the real question is not what 3I Atlas is. The real question is what exactly. In the new data made so many experts pause at the same time. When data from the XMM Newton Space Telescope was quietly released, it introduced a problem few scientists were eager to confront directly. The instrument had detected faint but unmistakable X-ray emission associated with 3I Atlas. Not noise, not background contamination. A real signal, spatially aligned with the object itself, and persistent across multiple observation windows. At first glance, X-rays near a comet are not unheard of. In rare cases, weak X-ray glow can emerge when highly charged ions in the solar wind collide with neutral atoms surrounding a comet. This process, known as charge exchange, has been observed before within our solar system. But 3I Atlas was different in ways that made this explanation feel incomplete. Typical cometary X-ray emission follows predictable patterns. It scales smoothly with solar wind conditions. It produces diffuse, symmetrical halos. It behaves politely, as theory expects. The X-ray signal from 3I Atlas did not. Its intensity fluctuated in ways that did not cleanly track solar wind density. Its spatial structure appeared uneven, and its spectral profile refused to settle into a single, elegant explanation. Scientists could still make the equations work. but only by forcing parameters into uncomfortable corners. Ion densities had to be unusually high. Neutral gas distributions had to be oddly shaped. Interaction regions had to be positioned just right. None of these assumptions were impossible, but together they formed a picture that felt increasingly strained. What made the situation more unsettling was what the data did not show. There were no signs of instrumental error, no calibration anomalies, no background sources masquerading as signal. Independent checks confirmed the detection. Different processing pipelines arrived at the same conclusion. The X-rays were real, and they were coming from where 3I Atlas was moving through space. This marked the first time such a mission had been confidently associated with an interstellar object. Unlike comets born inside our solar system, 3I Atlas arrived carrying a physical history shaped by another star. Another disk. Another environment entirely. That alone raised a quiet but profound question. Were scientists witnessing a familiar process acting on unfamiliar material, or an unfamiliar process acting in plain sight? X-ray photons do not lie easily. They require energy. They require interactions violent enough to shake electrons from atoms. When they appear where they should not, they demand an explanation that goes beyond coincidence. If this emission were merely accidental, it would fade neatly into the background of known physics. But it did not. It persisted. It repeated. And it aligned too well with the object itself to be dismissed. So the question becomes unavoidable. If the X-rays from 3I Atlas are not simply a statistical fluke, not a misidentified solar wind interaction, and not an artifact of instrumentation, then what mechanism is truly responsible for producing energy at a wavelength that was never expected to appear here? As 3I Atlas moved deeper into the heliosphere, it entered a region dominated by the solar wind. A constant stream of charged particles flowing outward from the sun. Under normal circumstances, when this plasma encounters a comet, the interaction is well understood. Neutral gas expands. Ions are picked up. Magnetic field lines drape smoothly. And the system settles into a familiar and predictable structure. But in the case of 3I Atlas, the plasma did not behave as expected. Measurements indicated a response stronger than models predicted. The solar wind appeared to slow more abruptly. The interaction region showed signs of compression rather than gradual coupling. Instead of flowing smoothly around a diffuse cloud of gas, the plasma behaved as though it were encountering something more resistant. Something with structure. This immediately raised doubts about the nature of the material surrounding the object. Classical cometary atmospheres are tenuous, irregular, and transient. They do not present sharp boundaries. They do not significantly redirect plasma flow on short timescales. Yet the signatures observed near 3I Atlas suggested a more coherent interaction. One that implied either an unusually dense composition or a geometry that plasma does not encounter in typical solar system comets. One possibility is chemical. Material formed around another star may contain ratios of elements and compounds rarely seen in our own system. Exotic ices, unfamiliar dust matrices, or bonding structures shaped by different radiation environments could alter how gas ionizes and how plasma couples to it. In this interpretation, the strange behavior is not intentional or engineered, but simply foreign. Another possibility is structural. If the object possesses an internal or surface geometry that is more ordered than expected, even without artificial origin, plasma would respond differently. Sharp gradients, layered materials, or partially solid surfaces could cause charged particles to pile up, deflect, or oscillate in ways that resemble interaction with a physical obstacle rather than a diffuse cloud. What unsettles scientists is that plasma does not react emotionally. It responds only to fields, charges, and matter. When its behavior changes, it is because something measurable has changed in the environment. In the vicinity of 3I Atlas, that change appears too pronounced to be dismissed as statistical variation. This does not imply intention. It does not require intelligence. But it does suggest that the object is not simply dissolving into space as it passes through. It is shaping the space around it, forcing energetic particles to adjust, to bend, and to respond, and that leads to an uncomfortable ambiguity. Are we witnessing an unfamiliar form of chemistry acting under extreme conditions? Or are we observing plasma responding to a physical structure that defies our expectations of what a comet should be? That distinction matters. Because chemistry expands existing models, while structure challenges them. So, the question remains unresolved. When plasma meets 3I Atlas and reacts as if encountering something solid, something organized, something resistant, are we truly seeing exotic matter from another star? Or are we glimpsing a form of architecture that nature rarely builds but does not forbid? As 3I Atlas continued its passage through the inner solar system, a subtle but striking change began to appear in its spectral signature. Observations showed a rapid increase in greenish-blue emission, a color shift that immediately drew attention because it was not driven by brightness alone, but by chemistry. The source of this color is linked to diatomic carbon, pronounced atomic carbon. This molecule is well known in comet science and is responsible for the characteristic green glow seen in some cometary comas. Under normal circumstances, diatomic carbon appears when carbon-bearing compounds are broken apart by solar radiation, and its intensity tends to scale reasonably well with proximity to the Sun. That expected relationship did not hold for 3I Atlas. The green emission intensified in a way that did not cleanly match its changing distance from the Sun. At times, the signal strengthened without a corresponding increase in solar heating. At other times, it appeared to plateau or localize rather than spreading smoothly through the surrounding coma. This behavior placed 3I Atlas outside the comfortable patterns established by decades of comet observations. Timing made the anomaly even harder to ignore. In typical comets, diatomic carbon emission rises gradually as volatile materials warm and sublimate. The onset is predictable, almost routine. In 3I Atlas, the appearance of the green glow arrived offset from those thermal milestones. It emerged neither early enough to suggest extreme volatility, nor late enough to follow conventional heating curves. Even more puzzling was how uneven the emission appeared. The green light was not distributed symmetrically around the object. Certain regions brightened while others remained relatively quiet, suggesting that the source of the carbon was not uniformly spread across the surface or within the surrounding gas cloud. This patchiness implies a non-homogeneous origin. There are conservative explanations. The material could be chemically diverse, with localized pockets richer in carbon-bearing compounds. Radiation damage accumulated during interstellar travel could have altered molecular bonds unevenly. Microfractures might expose fresh material sporadically. All of these processes are physically plausible, but together they begin to describe an object far more complex than a loosely bound mixture of ice and dust. The deeper issue is not whether diatomic carbon can exist here. It clearly can. The issue is why it appears when it does, where it does, and with an intensity that resists simple scaling laws. Each deviation alone could be explained away. Taken together, they form a pattern that suggests activation rather than gradual release. Carbon does not ignite spontaneously. It responds to energy thresholds. When those thresholds appear misaligned with solar input, scientists are forced to ask whether another mechanism is involved. Whether chemical, structural, or something not yet fully modeled. So the question sharpens. Why did carbon light up now? In this particular configuration? At this specific moment in the journey of 3I Atlas? And more importantly, what changed inside the object just before the green glow appeared? On November 30th, 2025, the Hubble Space Telescope returned its attention to 3I Atlas. The timing was deliberate. By then, earlier anomalies had already raised questions, and Hubble was not being asked to discover something new, but to look again with greater scrutiny. What it captured did not resolve those questions. It complicated them. The images revealed a dust coma that was distinctly asymmetric. Instead of expanding evenly around the nucleus, material appeared unevenly distributed, with one side showing denser scattering while other regions remained unexpectedly sparse. This alone was unusual, but not unprecedented. Comets can be messy. What followed, however, was harder to dismiss. Embedded within the coma were darker regions, areas where dust density appeared noticeably reduced, almost as if material had been removed rather than never emitted. These voids did not align naturally with solar radiation pressure or simple outgassing models. They suggested either directional clearing or a suppression of activity in specific zones. Even more puzzling were elongated structures extending away from the nucleus at angles that did not correspond to the expected dust tail direction. Under standard conditions, particles released from a comet are shaped by gravity and sunlight, forming predictable arcs and tails. The features seen around 3I Atlas resisted that geometry. They stretched, but not where they were supposed to. Hubble's data release was careful. The accompanying report emphasized imaging details, exposure parameters, and observational context. It avoided strong physical interpretation. No speculative language. No aggressive modeling claims. Just the facts. Presented with restraint. In the world of astrophysics, that kind of restraint often signals uncertainty rather than confidence. This caution stands out because Hubble has no reason to be modest when results are clear. When phenomena fit established frameworks, interpretation follows quickly. Here, it did not. The images were allowed to speak visually, while the text surrounding them remained deliberately neutral. That neutrality raises an important point. Hubble does not observe imagination. It records photons. When those photons outline shapes that do not align with expectation, scientists must decide whether the discrepancy lies in the object or in the model used to describe it. In this case, neither option feels comfortable. The asymmetry, the darkened regions, and the misaligned structures all suggest that 3I Atlas is not shedding material in a simple, uniform way. Something is shaping its environment unevenly, either from within the object or through interactions not yet fully understood. So the question remains open and unsettling. What exactly did Hubble see in those images that made interpretation so cautious, so carefully worded, and so incomplete? And what would those structures mean if they were not transient artifacts, but signatures of a process still unfolding? While most attention remained focused on dedicated observatories, another observer quietly entered the story. The JUICE spacecraft, operated by the European Space Agency, was never designed to study interstellar objects. Its primary mission lies far beyond this moment. Yet, when 3I Atlas passed through a favorable observational geometry, JUICE did not simply record a brief snapshot and move on. Using its navigation camera, NavCam, the spacecraft tracked activity associated with 3I Atlas over an extended period. This choice alone was notable. Navigation cameras are functional instruments, not precision science images. Time allocated to them is usually conservative. In this case, that caution was relaxed. The activity did not appear as a single transient flare. It persisted for hours. Brightness levels rose and fell in a manner that suggested repetition rather than decay. Instead of a steady fade expected from simple outgassing, the signal showed variations that hinted at a cyclical process unfolding in real time. Those variations immediately raise questions. Natural comet activity can fluctuate, but such changes are typically chaotic, driven by irregular surface exposure or gradual thermal evolution. What JUICE recorded appeared more organized. The intensity shifted, then returned, then shifted again, not randomly, but with a rhythm that was difficult to ignore. At present, the details of that rhythm have not been publicly released. No precise timing intervals, no confirmed period length, no statement linking the variations to rotation. Solar wind modulation, or instrumental cadence. The raw data remains closed, awaiting deeper analysis and cross-comparison with other datasets. That absence of detail matters. In planetary science, periodic behavior is rarely meaningless. Cycles often point to rotation, structural asymmetry, or recurring physical processes. When a signal repeats, it implies a driver that is stable enough to act more than once. The fact that JUICE was not optimized for this observation only adds to the tension. If a navigation camera can detect cyclical variation, the underlying signal must be strong enough to rise above noise and operational constraints. That suggests the phenomenon is not subtle. For now, interpretation remains suspended. Without raw data, speculation is limited, but the implication lingers. Something associated with 3I Atlas was active long enough and consistently enough to imprint a pattern on the measurements of a spacecraft that was never meant to look this closely. And that leads to a difficult but unavoidable question. Does this cycle align with something familiar, such as rotation or plasma modulation? Or does it hint at a process operating on a timescale we do not yet recognize until the data is released? The rhythm remains unheard. But its presence alone has already changed how this object is viewed. At a certain point, the story of 3I Atlas stopped belonging to a single instrument or a single team. Instead, it became the focus of a coordinated observational effort involving Psyche, Hubble, JUICE, and the Trace Gas Orbiter. Such convergence is rare in comet science and almost unheard of for an object that poses no threat to Earth. This was not a response to danger. No collision trajectories, no impact probabilities, no emergency mitigation scenarios. The reason these spacecraft were asked to look at the same target was far more subtle and far more revealing. 3I Atlas represents a scientific opportunity that cannot be repeated. Unlike periodic comets or near-Earth objects, this body is not bound to the Sun. It arrived from interstellar space on a hyperbolic path and will leave the solar system forever. There will be no return pass. No second chance with better instruments. No opportunity to refine hypotheses after the fact. Whatever can be learned must be learned now. Each spacecraft contributes a different perspective. Hubble captures fine scale structure and optical behavior. Psyche provides tracking and context from deep space navigation. JUICE offers extended temporal monitoring from an unexpected vantage point. The Trace Gas Orbiter refines trajectory and environmental interaction near Mars. Individually, these datasets are informative. Together, they form a three-dimensional portrait across space, time, and wavelength. This level of coordination suggests that scientists are not merely cataloguing a curiosity. They are attempting to constrain a phenomenon before it escapes their reach. When multiple missions are aligned around a single transient object, it signals concern not about risk, but about understanding. The underlying motivation is simple and unsettling. Interstellar objects carry information about environments humans cannot visit. They are physical samples of other planetary systems, shaped by different radiation fields, different chemistries, and different histories. Most will pass unnoticed. 3I Atlas did not. The decision to mobilize multiple assets reflects an awareness that this object may be telling a story that will never be told again. Once it departs, only incomplete data and unresolved questions will remain. No future mission can chase it. No probe can be redirected in time. That urgency is not driven by fear. It is driven by the recognition that rare events often define scientific progress. Miss them, and decades may pass before another appears. So the question becomes unavoidable. If 3I Atlas were truly ordinary, why would so many independent missions be asked to watch it at once? As if the scientific community sensed that this brief passage might be the only window into something they have never seen before. As additional tracking data became available, attention turned to the object's trajectory. The trace gas orbiter provided a new layer of precision, allowing scientists to refine the path of 3I Atlas with far greater accuracy than before. Positional uncertainties shrank. Error bars tightened. On paper, the orbit became one of the best constrained ever achieved for an interstellar object. But precision did not bring comfort. It brought clarity. As the noise fell away, subtle deviations emerged more distinctly. Small residuals appeared in the motion, not large enough to trigger alarms, but persistent enough to resist elimination. These were not dramatic course changes. They were slight discrepancies that survived repeated refinements and recalculations. In earlier stages of analysis, such deviations could be dismissed as observational uncertainty. Now that explanation no longer held. With improved data quality, the anomalies did not vanish. They became sharper, more defined, almost framed by the very models designed to suppress them. This is where orbital mechanics becomes unforgiving. When a trajectory is well constrained, any remaining deviation must be accounted for. Gravity alone should dictate the path. Outgassing can introduce non-gravitational forces, but those forces tend to produce smooth, predictable accelerations aligned with solar heating and rotation. The deviations seen here did not fit that pattern cleanly. Attempts to absorb the discrepancies required uncomfortable assumptions. Highly localized jets firing at precise orientations. Rapid changes in activity without corresponding thermal triggers. Force vectors that shifted in ways difficult to reconcile with a simple rotating body. None of these explanations were impossible, but none were satisfying. What makes this situation unusual is not the size of the anomalies, but their persistence. Small effects are often the most revealing because they survive refinement. When every major variable is controlled, what remains carries disproportionate significance. The refined orbit of 3I Atlas does not suggest chaos. It suggests consistency interrupted by something subtle, something acting gently, repeatedly, and just strongly enough to leave a trace without overwhelming the system. That raises a critical distinction. Random noise disappears with better data. Systematic effects do not. The more precisely the orbit is measured, the more clearly these residuals stand apart from expectation. So the question sharpens once again. If the trajectory of 3I Atlas is now known with high confidence, and gravity alone cannot fully explain its motion, what is introducing these small but stubborn deviations, and more importantly, are we observing the last unresolved imperfections of our measurements? Or the first measurable influence of a process we have not yet learned how to describe as orbital refinements accumulated? A deeper issue began to surface beneath the discussion of small deviations. The motion of 3I Atlas appeared to include components of acceleration that could not be fully accounted for by gravity alone. This was not unprecedented in comet science. But the usual explanation began to feel increasingly insufficient. Non-gravitational acceleration is typically attributed to outgassing, as volatile materials sublimate. Jets of gas act like microscopic thrusters, subtly altering an object's velocity. This mechanism has explained countless cometary behaviors within the solar system. for 3I Atlas. However, applying this framework required assumptions that stretched credibility. To match the observed motion, models had to invoke extremely uneven gas emission. Jets would need to activate at precise locations, with carefully oriented directions, and with intensities that changed rapidly over short timescales. The object would have to possess dramatic internal asymmetries, yet maintain overall structural stability while traveling through interstellar space for millions of years. Another option was to assume highly variable density. Regions of the object would need to differ significantly in mass and composition, allowing small forces to produce disproportionate acceleration. While not impossible, this picture conflicts with expectations of gradual erosion and homogenization over long cosmic timescales. What becomes uncomfortable is not that these explanations fail outright, but that they require stacking multiple unlikely conditions at once. Each assumption is defensible in isolation. Together, they form a model that feels increasingly artificial, designed to preserve familiarity rather than confront anomaly. This exposes a quiet weakness in current approaches. Outgassing has become a catch-all solution, flexible enough to explain almost any deviation if parameters are adjusted far enough. That flexibility is both its strength and its danger. When a model can explain everything, it risks explaining nothing. What is rarely discussed openly is the alternative. If outgassing alone cannot account for the acceleration, then another mechanism must be contributing. That mechanism does not need to be exotic or intentional. It could involve electromagnetic effects, interaction with charged dust, or structural properties that alter momentum exchange in ways not yet well characterized. These possibilities remain underexplored, not because they are forbidden, but because they complicate established frameworks. They demand new simulations, new assumptions, and new uncertainties. It is far easier to push existing models harder than to admit their limits. Yet, the data does not negotiate. The acceleration is there. It is small, persistent, and resistant to simplification. Ignoring it does not make it disappear. So, the question must be asked carefully. But honestly, if gravity and conventional outgassing cannot fully explain how 3I Atlas is moving, what possibility are we quietly avoiding by insisting that they must? As observations accumulated across different instruments and angles, attention began to shift from motion to form. The way 3I Atlas reflected light did not behave as a simple, randomly shaped body would. Instead of smooth brightness variations expected from an irregular but amorphous surface, the reflected signal showed abrupt changes, as if light were interacting with flatter regions or sharper edges. This pattern is difficult to reconcile with the classic image of a loosely bound icy nucleus. Natural cometary surfaces tend to be chaotic. They are eroded unevenly, fractured randomly, and softened by sublimation. Sharp geometric features do not usually survive long in such environments. Yet, the photometric data from 3I Atlas hinted at something more ordered. One explanation is that the object is rocky rather than icy. Solid rock can maintain edges and planar facets more effectively than volatile rich material. However, this introduces another problem. rocky bodies of the size implied by the brightness data should not remain so intact after prolonged exposure to interstellar radiation. Micrometeoroid impacts and thermal cycling over millions of years. Those processes tend to round and fracture even the hardest materials. Another possibility is that the object is dominated by ice, but of an unusually durable kind. Certain exotic ices formed under extreme conditions could, in theory, possess higher structural strength than those commonly found in the solar system. Yet even this scenario struggles to explain the persistence of distinct reflective geometries. Ice sublimates. It erodes preferentially. It rarely preserves clean boundaries. What makes both explanations unsatisfying is not that they are impossible, but that they fail in opposite ways. Rock explains the geometry, but not the longevity. Ice explains the longevity, but not the geometry. Each hypothesis solves one part of the puzzle while deepening another. This tension suggests that the surface of 3I Atlas may not be well described by a single material assumption. It could involve layering, internal reinforcement, or composite structures that respond to stress differently across scales. Such configurations are rare in known comet populations, but are not forbidden by physics. The challenge lies in recognizing that geometry itself carries information. Light reflects differently from smooth curves than from flat planes. It scatters unpredictably from jagged rubble, but predictably from organized surfaces. When reflection patterns repeatedly suggest order, scientists must consider whether that order is accidental or fundamental. This does not imply design in the intentional sense. Nature is capable of producing structures that appear optimized without purpose. Crystal lattices, basalt columns, and planetary rings all demonstrate this. But such structures arise under specific conditions, and those conditions leave signatures. So the question becomes unavoidable. What environment? What formation process? Or what evolutionary path could produce an object with surface geometry that appears neither fully random nor easily eroded, while surviving the long and violent journey through interstellar space? And if we cannot yet answer that, are we prepared to admit that our assumptions about what interstellar objects should look like may be incomplete when 3I Atlas is placed alongside the only 2 interstellar visitors studied before it? The comparison becomes impossible to ignore. Each object tells a different story, and none of them align cleanly. Oumuamua arrived first and shattered expectations by what it lacked. There was no obvious coma, no persistent gas emission, no classic cometary tail. Yet its motion suggested non-gravitational acceleration. Scientists were forced to explain acceleration without visible outgassing, leading to a cascade of speculative models and unresolved debate. Oumuamua became famous not for what it did, but for what it refused to show. Borisov, by contrast, behaved almost reassuringly. It displayed gas, dust, and activity that fit comfortably within known cometary frameworks. Its chemistry was familiar. Its behavior scaled predictably with solar heating. Aside from its interstellar origin, Borisov looked like a comet that simply formed somewhere else. It expanded the sample size without challenging the rules. 3I Atlas does neither. Unlike Oumuamua, it clearly shows gas and dust. Unlike Borisov, that activity does not behave cleanly. 3I Atlas emits X-rays. It develops a green glow associated with diatomic carbon. It interacts strongly with plasma. Its activity timing resists simple thermal explanation. Its acceleration cannot be reduced to a single mechanism without strain. Placed on a spectrum, Oumuamua sits at one extreme. Silent, but dynamically strange. Borisov sits at the other. Chemically active, but dynamically ordinary. 3I Atlas occupies an uncomfortable middle ground. It is active, but not predictably so. It is energetic, but not transparently driven by solar input. It is visible, but not easily categorized. This combination creates a profile that has not been seen before. Gas plus X-rays plus asymmetric structure plus subtle non-gravitational acceleration form a set of traits that no existing category fully accommodates. The object refuses to behave like a pure asteroid, a classical comet, or a simple hybrid. What this suggests is not that earlier interpretations were wrong, but that the sample size has finally reached the point where diversity can no longer be ignored. Two objects can be treated as anomalies. Three begin to hint at a population. Interstellar space is vast. Planetary systems form under a wide range of conditions. There is no reason to expect that all expelled material should converge into a single behavioral class. 3I Atlas may represent a transitional object, or it may be the first clear example of a category that has simply never been observed before. Classification systems are built on repetition. Without enough examples, they remain fragile. 3I Atlas presses directly on that weakness, forcing scientists to ask whether the current taxonomy of small bodies is incomplete when applied beyond our solar system. So the question now takes on a broader scope. Are we still dealing with variations of familiar objects? Or has 3I Atlas revealed the existence of an entirely new class of interstellar body that science has not yet learned how to name? As the anomalies surrounding 3I Atlas accumulated, one explanation began to surface more frequently than others: cryovolcanism. The idea is familiar in planetary science. Under certain conditions, volatile, rich bodies can experience eruptions of supercooled material, expelling gas and ice without requiring high temperatures. On paper, it offers a convenient way to explain activity far from the Sun. Applied to 3I Atlas, cryovolcanism does provide partial relief. It can account for episodic outgassing without continuous heating. It can explain localized jets emerging from specific regions rather than uniform sublimation across the surface. It even offers a mechanism for variability that does not strictly follow solar distance. But the relief is incomplete. Cryovolcanism does not naturally produce X-ray emission. It does not supply the energetic ion interactions required to explain the observed high-energy photons. To make that connection, additional assumptions must be layered on top, turning a once elegant idea into a composite workaround. It also struggles with timing. Cryovolcanic activity tends to respond to internal pressure buildup and structural failure. Such processes can be sporadic, but they do not usually settle into repeating cycles without a stabilizing driver. The apparent rhythmic variations hinted at in the data remain unaddressed. The asymmetric dust structures seen by Hubble present another problem. Cryovolcanic vents could create directional features, but sustaining large-scale asymmetry over time would require a stable orientation or persistent internal geometry. That begins to blur the line between random fracture and organized structure. What makes cryovolcanism attractive is not that it fits all observations, but that it fits just enough of them to feel necessary. It preserves a natural origin. It stays within known physics. It allows researchers to avoid invoking unfamiliar mechanisms while acknowledging unusual behavior. This is where caution is required. A hypothesis that explains some features while quietly ignoring others can become a patch rather than a solution. Each unexplained element is deferred, not resolved. Over time, the model grows heavier, burdened by exceptions and auxiliary assumptions. Cryovolcanism may indeed be part of the story of 3I Atlas. It may describe one layer of activity occurring beneath the surface, but treating it as a complete explanation risks mistaking plausibility for completeness. Science advances not by finding ideas that can survive scrutiny, but by finding ideas that reduce complexity rather than manage it. At present, cryovolcanism does not simplify the picture. It compartmentalizes it. So the question remains unresolved. Is cryovolcanism revealing a genuine internal process within 3I Atlas? Or is it serving as a necessary placeholder? A way to postpone confronting mechanisms that lie just beyond the reach of current models until those gaps are closed. The distinction matters. As scientists continue to align observations across instruments, one inconsistency became increasingly difficult to ignore. The timing of activity on 3I Atlas did not correspond cleanly with thermal expectations. It did not intensify exactly when solar heating should dominate. Nor did it lag in a way that could be explained by delayed conduction. Instead, it arrived offset, neither early nor late, but distinctly misaligned. In classical comet physics, activity follows temperature. As a body approaches the sun, volatiles warm, sublimate, and escape. The curve is familiar. Distance decreases, activity rises. 3I Atlas refused to follow that curve. Its strongest signals emerged at moments that did not correspond to obvious thermal thresholds. This kind of behavior is rare because temperature is a reliable driver. Even complex internal structures eventually respond to heat. When an object appears to activate independently of solar input, scientists must consider whether another threshold is being crossed. One unrelated to distance alone. The idea of an internal activation boundary begins to take shape here. Rather than responding smoothly to increasing energy, 3I Atlas behaves as if it remains dormant until a specific condition is met. Once crossed, activity turns on decisively. This suggests a mechanism governed by state rather than gradual change. Such mechanisms are uncommon in small bodies. They require internal properties that remain stable across a wide range of external conditions, then transition sharply. Phase changes, pressure thresholds, structural failures, or electromagnetic coupling could all, in theory, create such behavior. But none are easily demonstrated at this scale. What makes this particularly troubling is that the trigger does not appear to be unique to a single observation. The pattern persists across datasets, implying consistency rather than coincidence. That consistency rules out many random explanations and forces attention toward processes that are repeatable and constrained. If solar heating is not the sole driver, then the sun is no longer the master clock for this object. 3. iAtlas would be operating under a rule set partially decoupled from its environment. That alone challenges assumptions embedded deeply in cometry models. This does not imply agency. It does not require intent, but it does suggest regulation. Something defines when activity begins and when it remains suppressed, regardless of how smoothly conditions change around it. And that leads to a question science is not yet comfortable answering. If the timing of activation is not dictated entirely by the sun, then who or what is setting the threshold that tells 3iAtlas when to wake up, as datasets from different instruments were laid side by side? A subtle pattern began to surface. It was not obvious, not strong enough to declare a discovery, but persistent enough to resist dismissal. Certain signals associated with 3iAtlas appeared to repeat. Slight rises and falls. Gentle returns. Variations that did not fully fade into randomness on their own. Such fluctuations would mean little. Space is noisy. Measurements drift. Small bodies behave erratically, but repetition changes the interpretation. When a feature reappears, even faintly, it invites the question of rhythm. The problem is that the rhythm does not match familiar clocks. It does not align with simple rotational periods. If rotation were responsible, the cycle would be more stable and more easily identifiable. Instead, the timing appears irregular yet constrained, repeating without locking cleanly to spin. It also fails to match models based on volatile ice behavior. Sublimation-driven processes tend to respond smoothly to heat input and surface exposure. They do not naturally produce gentle oscillations that re-emerge without obvious external prompting. The observed pattern lacks the thermal signature such models predict. This places the phenomenon in an uncomfortable space between order and noise. Too structured to ignore. Too weak to define. A pattern that exists just above the threshold of confidence. What makes this particularly intriguing is consistency across context. The hints of repetition appear in different observational modes, suggesting that the signal is not an artifact of a single instrument or processing method. Each dataset alone is inconclusive. Together, they suggest something persistent. If a cycle exists, it implies a regulating process. Not necessarily a purpose-driven one, but a mechanism capable of pacing activity. Internal stress release, charge buildup and discharge, structural flexing, coupling with external fields. These are all physically plausible, yet rarely invoked at this scale. Nature does produce rhythms without intention. Pulsations, oscillations, resonances. But those rhythms usually leave clear fingerprints. Here, the fingerprint is faint, almost reluctant to be seen. That reluctance forces restraint. No claim of periodicity can be made yet, but the presence of repetition cannot be ignored either. It occupies a narrow corridor between coincidence and structure. So the question remains open, but sharpened. If 3i Atlas is indeed pulsing, even weakly, what process is setting that tempo? And why does it refuse to synchronize with the mechanisms we already understand? As reports surrounding 3i Atlas accumulated, one pattern stood out as clearly as any physical measurement. The language used to describe the object was unusually restrained. Official statements favored neutral phrasing. Observations were presented carefully. Interpretations were delayed or avoided. And one word, in particular, was conspicuously absent: anomaly. In scientific culture, this is not accidental. Words matter. Anomaly signals deviation from expectation. It invites scrutiny. It attracts speculation. And once introduced into public discourse, it is difficult to contain. NASA understands this better than most institutions. Instead of highlighting irregularities, reports focused on description rather than interpretation. What was seen, when it was seen, and how it was measured. Rarely why it might be happening. Language was calibrated to inform without provoking, to acknowledge uncertainty without amplifying it. This approach is familiar. When data is incomplete, restraint protects credibility. When multiple explanations remain viable, neutrality prevents premature commitment. And when findings touch sensitive conceptual ground, careful wording becomes a form of risk management. NASA does not deny the unusual aspects of 3i Atlas. It does not affirm them either. It allows the facts to exist without labeling them. This is not avoidance. It is containment. By refusing to name something an anomaly, the agency keeps the conversation within controllable bounds. Such caution often appears when results challenge established frameworks but have not yet crossed the threshold of reproducibility. It can also appear when interpretations risk being misused or sensationalized beyond their evidentiary support. In either case, silence is strategic. What makes this notable is consistency. Across multiple releases, across different instruments, the same tone persists. No single report breaks ranks. No press language escalates. This suggests coordination rather than coincidence. In science, anomalies are not feared. They are valued, but they are also powerful. They demand explanation, funding, and attention. Naming one too early can distort the process that follows. Naming one too late can erode trust. So NASA walks a narrow path. It presents the data, it acknowledges complexity, and it avoids words that would force a narrative before the evidence demands it. That leaves observers with a final, uncomfortable question. What characteristics of 3i Atlas make its behavior significant enough to warrant such linguistic discipline? And what exactly is being protected by keeping the conversation so carefully controlled? One of the most striking aspects of the response to 3i Atlas is what has not been said. There have been no warnings, no alerts, no statements hinting at danger, no mention of collision risk or planetary threat. In public terms, everything appears calm, yet behind that calm lies an intensity of observation that tells a different story. Multiple instruments continue to monitor the object closely. Tracking is persistent. Coverage spans wavelengths, distances, and perspectives. This level of attention is not routine. It requires coordination, time allocation, and prioritization. And it is being sustained without any narrative of urgency directed at the public. There is no contradiction here. In space science, danger and importance are not the same thing. An object can be harmless and still demand extraordinary scrutiny. The absence of threat simply removes one motivation. It does not eliminate others. 3I Atlas is being watched not because it might do something to us, but because it may be telling us something we cannot afford to miss. Its value lies in information, not impact, whatever it represents. It is fleeting. Once it leaves the solar system, the opportunity vanishes. This distinction matters. Hazard-driven observation is reactive. Discovery-driven observation is proactive. The latter often unfolds quietly, without dramatic language, because its consequences are long-term rather than immediate. What appears to be happening here is prioritization without publicity. Scientists are treating 3I Atlas as a high-value target, while carefully separating that judgment from public alarm. This allows investigation to proceed without distraction, speculation, or pressure to conclude prematurely. Such behavior usually signals that the importance of the object exceeds its ability to be explained quickly. When understanding lags behind observation, the safest course is to watch, record, and defer interpretation. In this context, silence is not reassurance. It is focus. That focus raises a question more revealing than any warning ever could. If 3I Atlas poses no danger, yet commands such sustained attention, then who exactly considers this moment critical? And what kind of knowledge are they determined not to lose? At its core, the mystery of 3I Atlas reduces to a deceptively simple question. What kind of thing is an interstellar object supposed to be? The most conservative answer is that it is debris, a remnant from another star system, ejected during the chaotic early stages of planet formation. In this view, 3I Atlas is no different in principle from asteroids and comets in our own system, merely displaced by gravitational violence and sent drifting through interstellar space. This explanation is comforting because it requires no new categories, only distance. Another possibility is more dramatic. 3I Atlas could be a fragment of a dead or disrupted planet, material torn from a planetary crust, mantle, or deep interior during a catastrophic event. Such fragments would carry unusual compositions, extreme structural properties, and histories shaped by forces rarely encountered by small bodies. This scenario is plausible, but statistically rare. A third option pushes probability even further. The object could be a product of processes so uncommon that they rarely leave detectable remnants. Exotic formation pathways, extreme radiation environments, or prolonged exposure to conditions that fundamentally alter matter. In this case, 3I Atlas would not be representative of a population, but a statistical outlier. a 1 in millions survivor. All of these hypotheses share a common weakness. Their likelihood is low. Interstellar space is vast, but detectable objects are few. Each candidate explanation occupies a narrow slice of probability. Yet, those probabilities are not equal. Some demand fewer coincidences than others. Some require fewer assumptions. Some align more naturally with the data. What becomes uncomfortable is that one class of explanation receives noticeably less attention than the rest, not because it violates physics, but because it violates intuition. It challenges how humans categorize natural objects and forces reconsideration of what counts as ordinary when the frame of reference expands beyond a single star system. Science prefers messengers to mysteries. A messenger carries information from a known context. A fragment fits neatly into a narrative of destruction and dispersal, but a truly unfamiliar product, one that does not map cleanly onto existing categories, demands a conceptual shift. 3I Atlas sits precisely at that boundary. It can be framed as debris. It can be framed as a relic. Or it can be framed as something that does not yet have a comfortable label. None of these interpretations are forbidden. But one of them requires scientists to admit that the inventory of natural objects may be more diverse than previously assumed, even at the smallest scales. And that leads to the hardest question of all. Among the competing hypotheses for what 3I Atlas truly is, which one unsettles us, not because it is unlikely, but because it forces us to reconsider what kinds of objects the universe is capable of producing at all. There is an important distinction that often becomes blurred in discussions about unusual objects. 3I Atlas does not transmit signals. It does not broadcast information. It does not act with intention. In every measurable sense, it is passive. And yet, its presence consistently provokes reactions that are anything but ordinary. The surrounding environment changes because the object is there. Plasma behaves differently. Radiation interactions intensify or distort. Emissions appear where models do not predict them. These effects are conditional. They do not occur everywhere. They occur when specific thresholds are met. When certain interactions are triggered. When the object enters particular regimes of energy and field strength. This kind of behavior does not require agency. A lightning rod does not decide to attract lightning. It does so because of its structure. A catalyst does not choose to accelerate a reaction. It does so because of its properties. In physics, response without intention is common. What is rare is response that is both selective and persistent. 3I Atlas appears to operate in that narrow space. It does not initiate action, but it reshapes outcomes. Space around it behaves differently than space elsewhere, as if encountering a material configuration that alters the rules of engagement, not breaks them, but bends them. This suggests that the object possesses physical characteristics that are unusually well matched to its environment. Composition, geometry, internal structure, and surface properties may combine in a way that amplifies interactions. None of this implies intelligence. It implies rarity. Natural processes are capable of producing extreme outliers. Crystals form with perfect symmetry. Neutron stars compress matter beyond intuition. Planetary rings settle into resonant order. These structures emerge without design, yet appear optimized for specific behaviors. The discomfort arises when optimization appears where randomness is expected. When an object formed through chaotic processes displays properties that consistently elicit strong, conditional responses. Scientists are forced to ask whether their assumptions about typicality still apply. 3i Atlas may simply be an edge case, a configuration so uncommon that it has never been observed before. But edge cases matter. They test the limits of models built on averages and expectations. If this object is not acting, but is nevertheless causing space to act around it, then its significance lies not in intent, but in constitution. It is not a messenger choosing to speak. It is a structure that forces interaction, and that leads to a deeper question, one that physics cannot easily dismiss. How rare can a naturally formed object be? Before rarity itself begins to challenge our understanding of what natural processes usually produce. As scientists attempt to reconcile the behavior of 3i Atlas with physical models, one possibility keeps resurfacing quietly. The object may be far less dense than its apparent stability suggests. Several simulations only converge when density values are pushed unusually low. At first, this seems contradictory. Low-density objects are expected to be fragile, easily disrupted by tidal forces, radiation pressure, and thermal stress. Yet 3i Atlas shows no sign of structural collapse. It remains coherent while exhibiting activity and interaction that would destroy a loosely bound body. This paradox points toward a specific class of structures. Hollow or highly porous configurations can possess low average density while maintaining surprising mechanical strength. In such systems, internal voids distribute stress rather than concentrate it. Shock waves dissipate. Fractures do not propagate easily. The structure bends instead of breaking. Within our solar system, such architectures are uncommon. Most cometary nuclei are rubble piles, loosely aggregated and weakly bound. Their porosity arises from randomness, not optimization. Over time, repeated heating and erosion tend to degrade whatever internal coherence they possess. Interstellar travel changes the equation. Objects ejected from their parent systems are subjected to extreme selection pressures, radiation, collisions, and time eliminate the fragile. What survives is not typical. It is resilient. A hollow or foam-like structure could offer exactly that advantage, absorbing energy without disintegrating over millions of years. This would also help explain several observed anomalies. Low density could amplify non-gravitational acceleration. Internal cavities could regulate gas release, creating delayed or episodic activity. Structural anisotropy could shape asymmetric dust and plasma interactions. None of these effects require new physics. They require uncommon architecture. The difficulty lies in formation. How does such a structure arise naturally? Hollow configurations do not form easily through simple accretion. They imply either differential growth, internal erosion, or catastrophic processes that remove material while preserving an outer shell. These conditions are rare but not impossible in dynamic planetary systems. Once formed, however, such an object would be uniquely suited for interstellar survival. Light enough to be accelerated, strong enough to endure, stable enough to persist. In that sense, hollow structure is not an anomaly. It is an adaptation shaped by cosmic filtering. This perspective reframes the question. Instead of asking why 3I Atlas is unusual, we ask why we expected interstellar objects to resemble the fragile bodies we observe locally. So the mystery deepens. If 3I Atlas is indeed hollow or highly porous, then where did such a structure form? And what kind of environment is capable of producing objects that are light, strong, and resilient enough to cross the void between stars intact? Interstellar space is not empty in any meaningful sense. It is a hostile environment shaped by radiation, high-energy particles, micrometeoroid impacts, and relentless time. Objects that leave their home star systems do not drift gently. They are eroded, fractured, heated, and slowly dismantled over millions of years. Most do not survive. Small bodies with weak internal cohesion break apart. Volatile, rich objects sublimate away. Rubble piles disperse. Irregular fragments are ground down by collisions too small to notice individually, but devastating in accumulation. Interstellar travel is not a journey. It is a filter. And yet 3I Atlas arrived intact. Its survival is not trivial. It implies resistance to radiation damage that would normally alter chemical bonds and weaken material. It implies mechanical strength sufficient to endure countless micro-impacts without catastrophic fracture. It implies thermal stability across extreme temperature gradients experienced while drifting between stars. This does not mean the object was designed in the intentional sense, but it does suggest optimization in the physical sense. Certain configurations survive better than others. Certain combinations of density, structure, composition, and geometry are favored when exposure time approaches geological scales. In evolutionary biology, selection operates on organisms. In astrophysics, selection operates on matter. The interstellar medium eliminates the fragile and preserves the resilient. What reaches another star system is not representative of what was formed. It is representative of what endured. 3I Atlas appears to be a product of this brutal selection. Not average. Not typical. A survivor. This perspective reframes many of its anomalies. Unusual structure may be a consequence of survival rather than formation. Low density combined with strength may be a prerequisite for endurance. Irregular activity may reflect internal stress responses accumulated over cosmic time rather than fresh processes. If this is true, then 3I Atlas is not merely an object from another system. It is an object shaped by the journey itself. A record of what interstellar space allows to persist. That realization carries an implication that is easy to overlook. The population of interstellar objects we can observe is not a random sample. It is a biased one. It is dominated by extremes. So the question becomes unavoidable. If interstellar space acts as a filter, selecting only the most resilient configurations, then what properties does it favor? And what does the survival of 3I Atlas reveal about the kinds of structures the universe quietly preserves while everything else is erased? At this stage, it is important to draw a careful boundary. 3I Atlas does not require the word alien. It does not demand extraordinary explanations or speculative narratives. What it demands is something far more uncomfortable for science: an admission of incomplete understanding. The most honest statement that can be made is not that the object is artificial, but that it is unfamiliar. Not because it is complex, but because it originates from a context our models were never designed to handle. Most small body science is built on a single assumption that has quietly shaped decades of theory. Everything we study formed within one solar system. 3I Atlas violates that assumption. Its behavior is not strange in isolation. Each feature has a plausible explanation: gas release, non-gravitational acceleration, plasma interaction, structural resilience. The problem emerges when those features coexist. They do so in combinations rarely seen together, and in proportions that strain single system models. This does not point toward intelligence. It points toward difference. A body formed around another star would experience different radiation fields, different elemental ratios, different thermal histories, and different dynamical chaos. Expecting it to behave like a familiar comet is a category error. The absence of understanding is not due to a lack of equations. It is due to a lack of context. Our models are optimized for local conditions. They extrapolate outward cautiously. But they are not built for diversity across planetary systems. In that sense, 3I Atlas is not mysterious because it is complicated. It is mysterious because it is foreign in the literal astrophysical sense. It carries assumptions baked into its structure that our frameworks do not recognize. Science often advances not by discovering new forces, but by realizing that old assumptions were too narrow. The danger here is not misinterpretation, but overconfidence. Treating unfamiliar behavior as a failure of data rather than a limitation of perspective. 3I Atlas reminds us that nature does not standardize its products across the galaxy. Variation is not noise. It is information. So the real challenge is not resisting sensational explanations. It is expanding the conceptual scope of our science. Are our models flexible enough to describe objects shaped by entirely different stellar environments? Or are we still assuming that one solar system defines the universe as the investigation into 3I Atlas deepens? A more uncomfortable realization begins to surface. Many of the difficulties in interpreting this object do not stem from its behavior, but from the limitations of the frameworks being used to understand it. Modern comet models are overwhelmingly solar system centric. They are built from decades of observations of objects that formed under one star, within one protoplanetary disk, shaped by one radiation environment, and filtered by one gravitational architecture. These models are robust locally, but their assumptions quietly harden into defaults. Interstellar objects expose that rigidity. The fundamental problem is sample size. 3 objects do not constitute a population. Without a statistically meaningful number of interstellar visitors, patterns cannot be established and outliers cannot be confidently identified. What looks anomalous may be typical elsewhere. What appears extreme may be average under different conditions. There is also a lack of comparative baselines. When scientists say 3I Atlas behaves strangely, the implicit comparison is always to solar system comets, but that comparison may be invalid. It assumes that formation pathways, material composition, and evolutionary pressures are broadly universal. There is no empirical basis for that assumption. Statistics suffer as a result. Models rely on parameter tuning rather than constraint. When observations do not fit, parameters are adjusted instead of questioned. This keeps models functional, but it also masks the possibility that the wrong model is being applied altogether. 3I Atlas exposes this weakness without drama. It does not break the laws of physics. It simply fails to conform to expectations. And in doing so, it reveals how much of small body science depends on context that may not generalize beyond our own system. This is not a failure of observation. The data is rich. The instruments perform as designed. The failure lies in interpretation that assumes familiarity where none is guaranteed. Scientific frameworks are powerful precisely because they simplify. But simplification becomes distortion when applied outside its domain of validity. Interstellar objects force science to confront that boundary. The question is not whether 3I Atlas is strange. The question is whether it is strange at all, or merely exposing the fact that our theories are optimized for a narrow corner of the galaxy. And that leads to a necessary reckoning. Are we observing an object that defies classification? Or are we applying a classification system that was never meant to describe objects born under different stars? One question continues to surface among those following 3I Atlas closely. Why has so much of the raw data remained unavailable at first glance? The answer appears straightforward. Complex datasets require processing. Instruments must be calibrated. Signals must be separated from background noise. Cross-validation between independent teams takes time. In space science, patience is standard procedure. But that explanation only goes so far. In many cases, preliminary data is released with clear caveats. Uncertainty is acknowledged openly. Independent groups are invited to test interpretations. That process accelerates understanding. With 3I Atlas, the pace has been noticeably slower and more selective. Part of this caution is justified. When data is sparse and unprecedented, early interpretation can mislead. False patterns can spread faster than corrections. In such situations, controlling the flow of information protects scientific integrity. Yet control itself introduces tension. When raw data is withheld for extended periods, it narrows the range of voices allowed to examine it. Fewer eyes mean fewer perspectives. Alternative explanations are delayed. Unconventional interpretations are postponed, not evaluated. This is efficient, but it is not neutral. The underlying concern is not secrecy in the conspiratorial sense. It is narrative management. Once a dataset enters the public domain, interpretation cannot be reversed. Headlines form. Assumptions harden. Misunderstandings persist long after corrections are issued. For an object as unfamiliar as 3I Atlas, that risk is amplified. The boundary between careful skepticism and uncontrolled speculation is thin. Agencies are acutely aware of this. But restraint also carries a cost. Delayed transparency slows collective reasoning. It postpones the moment when independent verification can either dissolve anomalies or sharpen them. In extreme cases, it allows uncertainty to linger longer than necessary. This creates an uncomfortable trade-off. Release data too early and risk noise overwhelming insight. Release it too late and risk appearing to curate reality rather than reveal it. 3i Atlas sits precisely at that intersection. The data is valuable. The implications are uncertain. The audience is global. Every decision about timing shapes interpretation as much as content. So the question is not whether caution is justified. It clearly is. The question is, what caution is protecting against? Is the greater danger that uncontrolled analysis will generate confusion? Or that delayed openness will postpone a confrontation with conclusions that may be more unsettling than noise itself, and in the end, which is more threatening to science? Misinterpretation, or the slow realization that the truth does not fit comfortably within expectations. One of the most revealing aspects of the 3i Atlas story is not found in what is said, but in where the conversation stops. Major mainstream outlets such as CNN and BBC have reported on the object only at the surface level. Basic facts: discovery timelines, safe distance confirmations, and then silence. There is no extended analysis, no expert roundtables, no probing questions about inconsistencies, no exploration of why this object is being tracked so intensively across multiple missions. In media ecosystems that thrive on novelty and spectacle, this restraint is conspicuous. This absence is not the result of ignorance. Editors at these organizations have access to the same press releases, briefings, and expert networks as anyone else. They are fully capable of pursuing deeper angles. When they choose not to, it reflects editorial judgment rather than oversight. Mainstream science journalism operates under an implicit contract. Report what is confirmed. Avoid amplifying uncertainty. Do not speculate beyond consensus. This approach serves an important function, but it also creates blind spots. Stories that do not yet fit a clear narrative are often deferred until interpretation stabilizes. 3i Atlas sits in precisely that uncomfortable zone. It is scientifically significant, but conceptually unsettled. Its details invite questions that do not yet have clean answers. For mass media, this is an unattractive combination. It risks confusion without delivering resolution. There is also another factor. Certain topics become volatile when framed incorrectly. Interstellar objects already attract fringe speculation. Adding layers of unresolved complexity can trigger narratives that quickly escape editorial control. Silence becomes a form of containment. This does not require coordination or censorship. It emerges naturally from institutional caution, when the cost of misinterpretation outweighs the benefit of early coverage. Stories are paused rather than pursued. The result is a selective quiet, not denial, not dismissal, simply a decision to wait. But waiting has consequences. It leaves interpretation to smaller outlets, independent researchers, and online communities. It shifts the center of gravity away from established voices and into spaces where speculation fills the gap left by restraint. That dynamic raises a broader question about how scientific uncertainty is handled in public discourse. Silence can protect against misinformation, but it can also signal that something does not yet fit comfortably into accepted frames. So the question lingers beneath the headlines that never came. At what point does mainstream media decide that uncertainty itself is newsworthy? And what conditions must be met before silence is replaced by inquiry? At this point in the investigation, it is important to separate uncertainty from what is firmly established. Despite the unanswered questions, there are facts about 3I Atlas that are no longer in dispute. It is an interstellar object. Its trajectory is hyperbolic, unbound to the Sun, and consistent with an origin beyond the solar system. This conclusion is supported by independent measurements and refined orbital solutions. On this point, there is no scientific disagreement. It emits X-rays. The detection has been confirmed through careful analysis, cross-checked processing, and independent validation. Whatever the underlying mechanism, high-energy photons are present in association with the object. This is not an inference. It is an observation. It changes color. Spectral data clearly show the emergence and evolution of greenish emission linked to diatomic carbon. The shift is real, measurable, and temporally constrained. It reflects a change in chemical or physical conditions rather than an artifact of imaging. It exhibits activity that does not behave normally. Outgassing occurs, but not in a smooth or easily predicted manner. Plasma interactions are stronger than expected. Acceleration deviates subtly from purely gravitational motion. These behaviors are not speculative. They are documented. It is transient. 3I Atlas will not return. Its path ensures a single passage through the solar system, after which it will disappear into interstellar space. Beyond the reach of any current or planned mission, there will be no follow-up encounter. These points form the solid ground beneath the discussion. They do not depend on interpretation or theory. They are constraints that any explanation must respect. What makes this uncomfortable is how little certainty provides. Knowing what is happening does not explain why it is happening. The list of established facts narrows the range of acceptable models, but it does not select one. Science often progresses by expanding certainty until explanation becomes inevitable. Here, certainty accumulates without convergence. Each confirmed fact sharpens the puzzle rather than dissolving it. 3I Atlas is real. Its behavior is real. Its passage is real. And its departure is inevitable. So the question must be asked plainly. Are these certainties enough to understand the object? Or do they merely define the boundaries of a mystery that remains fundamentally unresolved? If the known facts define the boundaries of the problem, then what remains unknown defines its depth. And in the case of 3I Atlas, those unknowns are not minor details. They sit at the very core of the object's identity. The most fundamental uncertainty is material nature. We do not know what 3I Atlas is truly made of. Ice, rock, dust, exotic compounds, layered composites, or something unfamiliar formed under conditions we have never sampled. Spectral hints exist, but they do not converge into a definitive composition. Without that foundation, every higher level explanation remains provisional. The internal structure is equally opaque. Is the object solid? Fractured? Porous? Hollow? Layered? Or dynamically evolving from within? We infer structure indirectly through behavior, through how it accelerates, how it emits, how it resists disruption. But inference is not observation. The interior remains hidden. Then there is the question of activation. We do not know what initiates its activity. Thermal input alone does not suffice. Outgassing does not fully explain timing. Plasma interaction does not account for thresholds. Something switches on, but the trigger mechanism remains unidentified. Its formation history is also unknown. Was it assembled gently in a protoplanetary disk? Or violently during planetary destruction? Was it shaped by slow accretion? Catastrophic fragmentation? Or prolonged exposure to radiation and collisions? Each path leaves signatures, but we lack enough data to trace them backward. Even its stellar origin is unresolved. We cannot yet link 3I Atlas to a specific type of star or planetary system, metal-rich or metal-poor, young or ancient, quiet or violent. Without knowing where it came from, we cannot know what conditions it survived. And finally, there is the most philosophically uncomfortable unknown: purpose. Not in the sense of intention, but in the sense of role. Is 3I Atlas merely debris? A byproduct of chaos? Or does it represent a class of objects that naturally emerge under certain cosmic conditions? Does it exist only by accident? Or because the universe reliably produces such things and we are only now beginning to notice them? These unknowns are not empty gaps. They are structured absences. Each one limits interpretation and prevents closure. Together, they form a reminder that observation alone does not equal understanding. Science is often portrayed as a steady march toward answers. In reality, it is a negotiation between what can be measured and what can be inferred. 3I Atlas has pushed that negotiation to its limits, so the question becomes unavoidable. Looking at what we do not know, how many pieces of this puzzle are still missing? And how many of them might never be recovered once this object slips beyond our reach forever, when 3I Atlas finally leaves the solar system? It will do so quietly. There will be no farewell observation window, no final close pass, no dramatic last image. Its trajectory ensures that it cannot be followed, cannot be intercepted, and cannot be reached by any mission conceived today. Once it is gone, it is gone. There will be no opportunity to reobserve it under better conditions. No chance to test new hypotheses against fresh data. No way to correct early misinterpretations by direct measurement. Every unanswered question will remain unanswered. Frozen in time, what will remain is data. Images. Spectra. Light curves. Particle interactions. Orbital solutions. fragments of information collected under imperfect circumstances, limited by instrument capabilities and observational windows. That data will become the object itself, at least in scientific memory. From that point forward, understanding 3I Atlas will depend entirely on interpretation. Models will be refined, papers will be written, debates will unfold. Some explanations will harden into consensus. Others will be quietly abandoned, and some possibilities will linger indefinitely. Neither proven nor disproven, this is the uncomfortable reality of transient science. When an event cannot be revisited, interpretation carries unusual weight. Early assumptions can echo for decades. Initial framing can shape entire research directions. Errors, once embedded, are difficult to extract. 3I Atlas will not change after it leaves, but our understanding of it will. It will evolve as theories shift and as new interstellar objects are discovered. In hindsight, it may come to be seen as ordinary, or as the first hint of something far larger. That judgment will say less about the object itself and more about the trajectory of our knowledge. History often reclassifies mysteries not by solving them, but by contextualizing them within a broader pattern. When future scientists look back, they will not see 3I Atlas as it truly was. They will see it through the lens of what followed. So the question is not only scientific, but historical. When 3I Atlas is remembered years from now, will it be recalled as a curiosity we briefly observed, a puzzle we failed to resolve, or the moment when our understanding of interstellar objects quietly began to change as the observational window closes? An uneasy possibility begins to surface. That, despite all the attention, all the instruments, and all the analysis, something essential may still have been missed. No observation campaign is complete. Every telescope has limits. Every detector covers only a portion of the electromagnetic spectrum. It is entirely possible that 3I Atlas emitted signals outside the ranges we prioritized. Signals too faint, too brief, or too unconventional to trigger alerts. What is not measured leaves no trace. Timing matters just as much. Space is dynamic. Processes unfold on scales that do not wait for scheduled observations. A short-lived event, a transient interaction, or a rapid internal transition could have occurred between observation windows. If no instrument was looking at that moment, it effectively never happened. Then there are hypotheses. Science advances by asking questions. But it also advances by deciding which questions are worth asking. Some possibilities are set aside early because they seem unlikely, uncomfortable, or too costly to pursue with limited data. Others are postponed until better evidence appears. In doing so, certain explanatory paths quietly disappear. History is full of such moments. Signals dismissed as noise that later proved real. Phenomena ignored because they did not fit theory. Discoveries delayed not by lack of data, but by lack of imagination. From continental drift to pulsars, science has repeatedly underestimated what it was seeing. 3i Atlas sits uncomfortably close to that tradition, not because it demands a radical conclusion, but because it presents a dense cluster of small inconsistencies, each one individually ignorable, together suggestive of something incomplete. The danger is not error. Error is expected. The danger is premature closure, declaring understanding before all reasonable questions have been exhausted. Accepting a tidy explanation because the alternative feels too open-ended. Once the object is gone, the opportunity to correct that mistake vanishes. All that remains is interpretation layered on top of incomplete evidence. Future discoveries may fill the gaps, or they may expose them. So the question lingers with unusual weight. Have we truly extracted everything that 3i Atlas had to offer? Or are we about to repeat a familiar chapter in scientific history where significance was recognized only after the moment had already passed? And if this time feels different, is that because it truly is, or because every generation believes it will not be the one that looks back and realizes it missed something profound, viewed from a distance? 3i Atlas begins to resemble something more than an object of study. It functions as a test, not a test designed or announced in advance, but one imposed by circumstance, unfolding in real time across multiple layers of human knowledge. It tested our instruments first. Telescopes, detectors, navigation cameras, and orbital models were pushed to their limits by an object that did not behave as expected. Each anomaly forced recalibration, cross-checking, and careful reassessment of what the instruments were actually measuring rather than what scientists assumed they should measure. It tested our models next. Theories built on decades of solar system observations were applied outward, stretched, adjusted, and in some cases strained. Some held, others bent uncomfortably. A few revealed cracks that had always been there but never mattered until now. 3i Atlas did not break physics. It tested the boundaries of where our physics comfortably applies. It also tested scientific reflexes. How quickly do researchers default to familiar explanations? How often are parameters adjusted before assumptions are questioned? How readily is uncertainty acknowledged versus smoothed over? The response to 3i Atlas exposed habits as much as it exposed gaps. Then came the test of communication. Institutions chose restraint. Language was controlled. Data release was measured. Media coverage was cautious. This was not deception, but discipline. A balancing act between informing the public and preventing speculation from outrunning evidence. Whether that balance was optimal remains an open question. Finally, and perhaps most quietly, 3i Atlas tested humility. It confronted scientists with an object that could not be fully understood within the available time. It reminded observers that not every mystery resolves on schedule, and that some phenomena arrive not to be solved, but to reveal the limits of current understanding. There was no warning that this test was coming. No preparation. No rehearsal. The object arrived, passed through, and departed, leaving behind results rather than answers. In that sense, 3i Atlas did exactly what nature often does. It did not explain itself. It simply observed how we responded. So the final evaluation cannot be reduced to equations or plots alone. It must also ask a broader question. Faced with something unfamiliar, fleeting, and resistant to classification, did we adapt our tools and thinking quickly enough? Or did we rely too heavily on what had worked before? In other words, when the universe quietly administered this test, did we demonstrate curiosity, rigor, and humility in equal measure? Or are there lessons still waiting to be learned? The universe never explains itself. It does not offer footnotes, press briefings, or conclusions. It sends samples. 3I Atlas did not speak. It did not announce its arrival or justify its existence. It simply passed through our solar system, obeying the same physical laws as everything else, yet quietly refusing to behave the way we expected. In doing so, it left behind questions rather than answers. Questions about the limits of our understanding, about how far models built in one small corner of the galaxy can be stretched before they lose meaning, about how often we mistake familiarity for universality, and confidence for completeness. 3I Atlas exposed something deeper than an anomaly. It revealed how much of science depends not just on data, but on assumption, on the idea that what we have seen before defines what is possible. When something arrives from elsewhere, those assumptions are the first thing it challenges. This object did not overturn physics. It did not rewrite equations. It simply reminded us that reality is under no obligation to fit comfortably inside the frameworks we have constructed. Nature is older, broader, and more inventive than any single system of explanation. And perhaps that is the most important message it carried. Not that the universe is strange, but that it is larger than our imagination. That beyond the boundaries of what we know, there are forms, structures, and processes that do not announce themselves as extraordinary. They simply exist. 3I Atlas is gone now, moving back into the darkness between stars. We cannot follow it. We cannot ask it questions. We are left only with what it allowed us to see. And with the way we choose to interpret it, history will decide whether this moment was a footnote or a turning point. Whether 3I Atlas becomes a curiosity remembered briefly, or the first clear signal that our picture of interstellar objects was incomplete. But one question remains, echoing long after the object itself has vanished. If this was not the strangest thing the universe had to show us, then are we truly ready for whatever comes next?